Warning, this is going to be a super boring video if you're not interested in finding gold, or are such an experienced gold prospector that you can tell the difference between mineralized and unmineralized quartz. So to tell the difference between the mineralized and the unmineralized, I'm going to draw a simple picture so that you can actually see how the quartz veins are formed and why they look different. I'm going to draw a cross section through the earth. Now this is not to scale, this is just to show concepts. Okay, we're going across to red, and deep down in the earth we've got molten rock. Now this molten rock could be below the crust, it could be even further down than that, but this is where the high pressure, high temperature molten rock is, and this is all just sitting down here. Every now and then, sometimes for a multitude of reasons which I won't go into here, some of this magma, and the difference between magma and lava is magma is molten rock under the ground, lava is molten rock that flows on the surface. Apart from that, there's no difference. Okay, sometimes this magma will breach out through the magma changer, come up into the above country rocks and start to form what's called a magma chamber. There could be more than one of these, and they start filling up it with molten rock sitting there. Basically consider it as a big lake full of molten rock. Now, these are not small. These are millions and millions and millions of cubic meters of rock, sometimes into the cubic kilometers of molten rock sitting down there. And you can just imagine squeezing that volume of rock into the crust, layers of rock that make up the crust. Something is got to give. And so what happens is that at the surface starts to bow up above the magma chamber. It starts to rise up as a dome. This pressure and pushing upwards on the rock puts a huge amount of stress onto the rock. And so what starts happening is fault lines, lines of weakness start radiating out from the dome. From the magma chamber, I should say, not from the dome. And these can go in multiple directions, but predominantly upwards, because that's the area of least overburden pressure. Some of these lines of weakness, and I'll generally refer to them as faults, not all of them have to be faults, but these lines of weakness, these faults, can make it to the surface. Other times they'll appear as nice big long sheet-like planar structures that are in the ground. And other times they can be broken up, discontinuous structures. But there are zones of weakness. What can happen then, as you get, and I'm swapping back to the red, is that some of this magma inside here, I'll use this one here, can start to leak into these cracks. Now, these cracks are not all the same size. There's multitude of sizes. Some are going to be smaller than the width of a human hair. Some of them are going to be multi-meters across, some even more. And so the bigger ones are going to be zones of low pressure, and so that the molten rock down here, which is incredibly high pressure, should say under high pressure and high temperature, is basically going to squirt out and start to race up these lines of weakness, these fault zones. Some of them will reach the surface and some of them won't. Those that don't reach the surface may start to crystallize halfway up there and the pipe becomes blocked. Others that will make it all the way to the surface, and what can happen here is you get a volcano forming. Sorry for the badly drawn volcano. And the rock will bubble out onto the surface and run down the slope. And this can happen on again and on again and off again. So this can happen in multiple places, and you can have multiple volcanoes happening. The rock that comes up in these sort of chambers, like for example this one here, and it doesn't reach the surface. So what you end up with is a zone of crystallized magma. Now it's just like solid rock now, extending for a long period away through the surrounding rock, and it's cross-cutting through all the surrounding rocks. And when that is exposed and people see it, it's what geologically is called a dike. Okay, let's just get rid of that circle. Okay, back to the drawing. You can imagine with all this heat in the system, with the magma pumping up, stressed rocks, there's a lot of induced heat inside here. Now, everywhere pretty much around the Earth you go, you're going to find groundwater of various types. Now, this water can be there in multiple different forms. It can be like what's called meteoric water. This is when rain has fallen on the surface and it's slowly trickled its way down and forms, standard groundwater we see around the place. Other places can be the rock here is so hot that it basically starts to sweat the surrounding rocks. That is not a geological term, but I'm trying to give you that concept. And it drives the water out of the surrounding rock. And I'll just move the screen out of the way and I'll demonstrate why. So let's go back to another cross-section. So in this case, I'm going to be talking about continental drift. So here, Australia is moving north, and so imagine again a cross-section. So this is the Australia plate. There's some seawater out here, and as it gets further north, it runs into the Southeast Asia plate. Now that zone of crushing up of rocks and everything else where it runs into is, fun enough, is what causes the islands of Indonesia at the moment. So out here, you've got the Southeast Asia plate. But what is happening here, and I have to go back and redraw the Australia plate. What happens here is the Australia plate is actually going underneath the Southeast Asia plate. So we are moving this way with respect to them, and they moving this way with respect to us. Side bit of information, the Australia plate is moving at the fastest rate of all the plates on the planet at the moment. Currently it's moving north at 7.5 centimeters per year. That's about 1.5 inches in the old money. Doesn't sound like much, but within 5 or 10 years, maybe a bit longer, you'll find that most of your coordinate systems of what you recorded in GPS and stuff, if you go back to the original spot, won't be there anymore because the plates moved on. Okay, now if you're only going to record things to the nearest meter, nearest 10 meters, whatever like that, then it's probably not going to have much impact here. But if you imagine the impact on things like surveying and land boundaries and everything else, where you need to know where things are to the millimeter and the continent is moving, it makes for exciting times. So when this crustal sheet of Australia gets sucked down into the abyss, a lot of this must be green. A lot of the sea sediment sitting along the bottom, okay, go down into the crust with it as well. Those sediments naturally are high in seawater, and so that seawater is dragged down into the depths. So going back to our diagram as before, I'll need this space. So we've got, it's going back to the draw, and I'll go back to the green. So we've got a lot of water in the system, especially in these zones of the faulting magmas at the edges of continental plates, which Australia was at various times through its geological history. So this water in the system basically starts getting sweated out and brought towards these fault zones because it's a zone of low pressure. As this water moves through the country rock, it actually starts to dissolve and move minerals out of the surrounding country rock, and the water becomes more and more enriched in minerals. So especially in our case, we're interested in the precious metals. So like gold is found pretty much everywhere on the planet, but it's in such low concentrations, it's not worth mining or being even interested in about. But if you can leach that gold out over long periods of time, now these sort of events I'm talking about here don't happen in 10 minutes. These are happening over tens of thousands, if not tens of millions of years, depending on where you are around the world. So that water has a long time to leach through the system. As that water comes in from the outside, it starts to come in and move up these structures. As it moves up these structures, it encounters what's called a PT change, which is a pressure and temperature change. As they get closer to the surface, obviously the temperature drops because it's further away from the major heat source down the bottom, and then the amount of overburden above it is dropping, so the pressure is dropping. So you start to get mineralization, and I'll try and do it in maybe orange. Come on, you can swap colors. And so you start getting mineralization occurring inside these veins. It doesn't happen all at the same time, and not all minerals come out. So you might find that at the bottom of the vein is more of a concentration of one particular set of minerals, and as they move up, more different types of minerals get precipitated out. In our case, we're interested in gold. Gold moves up come out, being leached out of the country rock. It reaches the veins, and it starts moving up in this boiling hot solution, moving upwards. As it gets up, it encounters a PT change. And depending on that, it can start to precipitate out. But one of the other things that can cause it to come out of, well, two other things that can cause it to come out of solution is an intersection with favorable chemistry rocks, so predominantly any rocks that are rich in iron. The fluids will come up, start to react with the iron-rich rocks, and gold can come out of precipitation. So if you've got a band of iron-rich rocks, the fluids are moving through, you'll have an enriched zone of iron inside, of gold precipitation out there. The other area is when you get pressure changes that happen under the ground that are not purely related to depth of burial. Again, let me just move this diagram out the way. So go back to the black. So what can happen is the fault comes along, and it changes direction, does something like that. Okay. Now you may ask, why would the fault change direction? It can be because for a number of different reasons, but a common one is actually a change in rock composition. So it's gone through either a rock of much harder or higher density or lower density, and the fracture will start to basically refract. Think of it as the same way as you take a spoon and you put it in a glass of water, and the spoon looks like it bends. And then you pull it out and you know it's not bent, but you put it back in and it looks like it's bent. That's the light refracting through the water. And that's the same thing happening here. So now we have this bend in the quartz vein. I'll call it that for the moment. But just imagine that on this side of the quartz vein, it's moving that way. And this side of the quartz vein, this side of there's no quartz in here yet. This side of the structure, the fault zone, is moving, the top part is moving upwards, and the bottom half is moving down to the bottom left-hand corner. So what happens in this zone here? Because this bit is moving this way, this bit has to be moving that way, and this bit is moving that way, this bit has to be moving that way. So what happens here is this starts ending up as a zone of opening. It's commonly called a dilational jog. Now, they don't have to occur at such a sharp angle as I've drawn here. They can be quite just a slight variation in the strike or the dip or both. And so what happens is this inside here, again drawing in red, this bit here is a zone of low pressure because the rocks are under tension. They're actually being pulled apart. Now you can get, in small scale, you can get actually cavities in the ground, almost like a cave. What normally happens is you end up with what's called a breccia inside. There are lots and lots of broken up bits of rock that's been cemented together, almost like a concrete. And so, just getting rid of the eraser thing. So what we can get inside here is that the mineralization is going to come up the fault and suddenly hit this void. I'll use the word void. And so it's a zone of low pressure. The liquid pours in and starts to precipitate out. Now, a couple of things start to happen here, which is really interesting. One, as I said before, pressure change. But also it's a chance for the liquid to pool and stop for a minute before it gets pushed up the rest of the fault zone. So in that time, the quartz and the other minerals inside that cavity have a chance to precipitate out, form crystals, and other mineralization starts to occur, especially if it's reacting with the country rock as well. Okay, we're done with that. So that's what's called a dilational jog. So we've got these systems here, and you might have one coming up here, and it's, oops, it's supposed to be on the blue. One coming up here, it might bend, and you might have some mineralization occurring in there. One of the things that is like concerned geologists for a long, long time is this concept of gold that comes out of solution and starts to react with the country rock. So let's say we've got this iron-rich rock, gold-rich solution pumping through, and it starts to react with the country rock, and gold starts to precipitate out. I don't think any geologists have any problem with that. But after the first phase of mineralization is gone, and the fluid's still moving through, there's still gold-bearing solutions coming up the fault. But it can't react with the country rock anymore, because now there's a thin plate of gold on that country rock interface. So chemically and logically, you would suggest it just keeps moving past. And that is as thick as the gold's going to get. And that's fine, because that's in many cases, that's what you will see. When you work in an underground mine, that you'll see very thin layers of visible gold. And that's what it can occur as. But a new theory that came out about last year, maybe year before, basically says that quartz is a piezoelectric mineral. Basically means if you apply stress to it or hit it, it generates a charge. And so the theory goes is that earthquakes are causing gold to precipitate in places we never thought they would. So what is piezoelectric minerals? Fancy sounding word. We're all very familiar with piezoelectric crystals. Every time you press that starter on your gas barbecue, every time you press the little button on that gas starter gun you have for camping or on the gas stove at home, and it generates the little flame, that's caused by a piezoelectric crystal. How that works is a crystal inside there where a little hammer hits the crystal. That process generates a voltage. The voltage generates a spark. Spark lights the gas. So quartz is a well-known piezoelectric mineral. And the theory is going that as earthquakes occur, and they do not have to be mega earthquakes, but lots and lots of small aftershocks, seismic events, which this sort of system I'm drawing here would be full of them. Every time there's a pump of fluids through the system, there's more shocks as the rocks are stressing and cracking and breaking. And in places that quartz are getting hit, and that's going to cause a voltage, and the current theory is that would cause layers after layer after layer to come out of solution and bind to each other. This has a more appeal to many of the geologists because now we have sort of a somewhat believable physical and chemical model for formations of thick pieces of gold that can actually form gold nuggets. The depths that this mineralization has occurred at, and I'm back on my drawing picture again. So let's go back to the black. So gold mineralization around Australia didn't all occur at the same time. Over on the east coast, you're looking at mineralization occurred around about 350 to 450 million years ago. Some parts of North Queensland, gold mineralization occurred around the 1.8 billion mark. Here in WA, a lot of the gold mineralization occurred about 2.5 to 2.7 billion years ago. Yes, it's been fairly accurately, as you can call 2.5 to 2.7 billion an accurate time zone, but the best scientific measurements point to that time zone. But for when that time occurred, the difference from here to where the mineralization occurred was roughly about 2 to 10 kilometers deep. So 2 to 10 kilometers. That's a long way down. most of our almost all of our gold mines do not go down to that depth. Most of them are in the sub-kilometer range, maybe a bit more. So what this means is these things haven't moved up. What has happened is the soil and rocks in the above have been removed off the continent. So for a mineralized vein in this system to stick out above the ground, or even at ground level, that would have to mean somewhere between 2 and 10 kilometers of overburden has been removed, gone from the face of WA. Where's that dirt gone to? It's been eroded away and basically dumped in the ocean somewhere. So that is a lot of rock that's been moved away. And so this erosion then has multiple effects as well. And I'll come back to that one as well in a bit. I promised you earlier on to be able to tell the difference between mineralized and unmineralized quartz veins. Again, I'm going to move this picture out of the way. So what happens here is, let's say we've had a quartz vein being deposited here. It could be a totally unmineralized quartz vein. Now, the way to tell an unmineralized quartz vein, it's usually very, very white in color, very solid in nature, and it has no impurities whatsoever. No traces of iron, no traces of little sulfides, no black specks, no nothing. It is very, very white quartz. Depending on where you are in WA and which prospectors you speak to, whatever, you can either be called buck quartz, B-U-C-K, or hungry quartz, because there's nothing basically in it. So if you see quartz like that, there's zones of quartz coming through, but it does not mean there's a very good chance there's no mineralization in that. But as I said before, you get this magma chamber deep down the bottom, and it's pulsing fluids up through the system as the chamber at the bottom empties, refills with magma, sending more and more fluid up the system. So what you can get is this nice big buck quartz vein, and then you can get another vein forming on the side. Reason why they generally form on the side, and it could be both in the footwall and the hanging wall, is because of when another spate of fluid comes up, more stress is put on the system. And so more basically stresses are induced, and the stresses need to find the path of least resistance. And the path of least resistance usually is along a rock contact. So between the country rock, which is out here, and the quartz, which is inside here. And that's a zone of weakness because it's a contrast in compositions, minerals, and everything else. And so the fault line will just run up along this edge. Okay, the fluids will get pumped up this bit and could start to form out. Now, if this is a mineralized system or a mineralizing event, so in this case the fluid coming up is mineralized, what will happen, very much as I said before, one, the gold in the solution will come up, it will start to react with the country rock. If there is pulsating events of rocks coming up, of fluid coming up, and pulsating events of stresses, what you can end up is layer after layer after layer after layer after layer after layer of tiny bands of gold getting deposited inside the quartz. So drawing a better diagram here. Okay, so what we've got is the first event comes through and it deposits there's quartz and gold along this edge. Okay, another race comes through, it runs along this edge and gold is deposited along this edge. Another one comes in and it's along this edge. Now, a similar sort of thing could be happening out this side as well. So you end up with these what's called laminated quartz. There's different layers of laminations in the quartz. Now, it's very rare that you will see visible gold in quartz unless it's very rich. But the way to tell that it is minerals, the gold generally does not come up by itself. Gold likes to hang out with its friends. and gold loves to be associated with iron and especially some sulfides. And what you'll end up happening is inside this quartz vein here is lots of fine disseminated sulfides and some darker layers of concentrated sulfides and every chance of having some gold inside there. So what happens is that you're going to pick up a piece of quartz in the field, and it's either going to be as white as snow, or it's going to have inclusions in it, things in it. And so if your quartz is quite grey in colour and has black bands in it, then that is a sign that that piece of quartz that you're holding carried mineralized solutions from deep in the ground coming up. It doesn't mean that there's gold in that system, but there's a lot better chance of having gold in that sample than the one maybe a couple of 100 meters away, which was as white as a sheet of paper. So that's what you look for when you get out in the field. Now, when you do get out in the field, let's just clear this screen away. You will sometimes find quartz veins that stick out of the ground. China Wall in the north of WA is the classic example. So what you've got is a surface, oops, let's just change colour. So you've got a surface coming along and you've got a dirty, great, big, stonking quartz vein sticking out of the ground. Now, obviously not even drawn vaguely to scale, but that's what it is. It's a big chunk of quartz sticking out of the ground. It's nice and white and you can see it for a long distance away. But why is the quartz sticking above the ground and not the same level as the ground? It's because quartz pretty much is for all intents and purposes, is an inert mineral. It doesn't react with anything else. So it's not going to react with water, it's not going to react with chemicals and whatever that you'll find in most normal systems. Sure, it'll react with acids of various types, but that's extreme acids. So what do you find in this sort of case is the quartz came up and the country rock out here has been eroded down faster than the quartz is sticking on the side. And so you end up with these sheet-like structures, almost like walls sticking out of the ground, can be very tall sometimes. Looks like they're made of massive blocks of white material. And they're very impressive, don't get me wrong. But they're not that uncommon, and there are quite a few of them around WA. What do you happen? So the quartz in there doesn't react with anything, and nothing is causing it to fall apart. So it's nice and rigid and it sticks together. As soon as you start having some mineralization inside there, it can be either sulfides or some iron, or pretty much anything else. As this, and I'll go back to my other diagram. And I'm going to draw a quartz vein. Okay, so this is the surface, and there's trees on top. This is the layer of solid rock to oxidized rock. Oops. So it's going to range from the soil at the top to semi-decomposing rock at the bottom. Some of these places down here will be called the saprolite zone. So this quartz vein comes through, and I'm going to change it to red. So this is all quartz inside here. If there's mineralization inside there, inside the quartz vein, like the sulfides I talked about, what happens is that the groundwater that is pretty much everywhere starts to react with the mineralization inside the quartz vein, so the ions and the sulfides, etc. And as these minerals start to oxidize, some of them can change volume, or some of them just get washed out of the system. But these minerals, in many cases, are holding chunks of quartz together. And so you get these zones of weakness, and all of a sudden, where's my pen gone to? You end up with a chunk of quartz breaking off. And so you end up with this quartz vein starts to crumble and fall apart into small pieces. Initially, big chunks will fall off. That exposes more of the mineralization to the water and the groundwater and the oxide in the air. and then in turn starts to break the quartz vein down to bigger and bigger and bigger. So you may find that at the surface in this sort of situation, you would have big chunks of quartz going away to smaller pieces of quartz. So the bigger the quartz, usually the closer you are to the vein. Okay. With this for coming together like this, you'll find that strongly mineralized veins rarely, if ever, make it to the surface because they've been so broken apart by the weathering processes and the erosion that's taking place that the quartz basically starts to crumble apart. It can start with the big pieces and end up down into microscopic pieces. As this surface as well is eroded away, because WA is pretty much getting eroded all the time, this quartz starts getting exposed at the surface. Now, the iron minerals that were tied up with that quartz can actually start turning state and actually being reprecipitated again into like iron, different types of iron mineralization in the soil. So you start getting a good composition of black and white type sitting on the ground. I hope you've enjoyed this video, and if you find it of value, I'd love it if you give me a like. Please leave a comment at the bottom, and if you really enjoyed it, I would really appreciate if you would think about subscribing. Thanks guys, and I'll see you on the next video.